Metals can be tricky. Watch out for those, and hopefully you do great. Question number 3, we have draw the Lewis structure for chloroform CHCl3, and what are its electron pair molecular geometries, and what orbitals on the CH and Cl overlap to form the bonds involving these elements. Okay, so this one's a little bit tricky, but we have CH3Cl. Let's say it's Lewis for CHCl3, okay? And electron pair geometry and molecular geometry. And we also want to know what orbitals overlap. So, with this being said, let's first knock out the Lewis structure first. CHCl3, we have 1 carbon, 3 chlorines, and 1 hydrogen. So, that is 4 valence electrons plus 1 valence electron. That's 5 right now, plus 7 times 3, because there's 3 chlorines. So that's 21 plus 5. We're working with 26 electrons total. We put carbon in the middle again because carbon has the most unpaired electrons. So carbon, whoops, H, whoops, apologies, Cl, H, okay? And now let's go ahead and fill in the rest of the lone pairs. Hydrogen is completely satisfied being like that. Same with the carbon because it's already sharing 4 of its 4. Now the chlorine is now sharing 1 of its 7, which is why we need to add 6 more. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. 2, 3, 4, 5, 6, 7. Okay. And now let's check if we have the right amount of electrons. So around each chlorine is 6 more, and we have 4 bonds. So that's 4 times 4. Whoops, sorry, 4 bonds. So that's 4 times 2, which is 8. And then 6 times 3, which is 18. So 18 plus 8, that does indeed equal 26. So we're done with the electrons. We got that. That's good. The formal charges for each one, just to make sure. Carbon having a net formal charge of 0 looks like that, or just 4 bonds, which is what we have. And chlorine's formal charge of 0 is when it has 3 lone pairs and 1 bond, which each chlorine does have. And the hydrogen's formal charge of 0 is just when it has 1 bond, which is also what this looks like. So we have a formal charge of 0 throughout. So this indeed would be our Lewis structure for this. And the important thing is that yes, everything does follow the octet rule when it's applicable. Okay? So now it's asking for the electron pair and molecular geometries. Once again, let's look at the bonding pairs it has, or just pairs in general, and how many of those are bonding pairs and how many of those are lone pairs. So we have before we continue, this is all in reference to the central atom. So 1, 2, 3, 4. So that's 4 bonding pairs, okay? And 0 lone pairs. So right now we actually have enough information to say the electron pair geometry and molecular geometry. For the electron pair geometry, we just take the total of it. So 4 plus 0, so that's just 4 pairs in total. Okay, so we know that this is sp3 hybridized, and this would be tetrahedral for the electron geometry. And now for the molecular geometry, we just specify now what the breakdown is. As we said, we have 4 and 0, 4 bonding pairs, 0 lone pairs. So funny enough, the molecular geometry is also tetrahedral. Okay? And the last question asks, which orbitals overlap? Now this one is a little bit tricky, okay? So for this, we can say that for the hydrogen to the carbon, because hydrogen only has the s orbital, it's an s, and because the carbon, as we said, was sp3, I do believe is an sp3 overlap, and then the rest of them, the chlorines, are all just overlapping sp3. Now for this one, I'm most likely wrong, so I will refer to the colleague here to see exactly what they're doing. I know it's something like this, but I don't want to be leading anyone astray. We have exactly this. We have the Vesper theory is tetrahedral molecular geometry, and the electron pair geometry is tetrahedral. So that one is correct. Now, each CCl bond is formed by the overlap of sp3 hybridized orbital on the C atom with a 3p orbital on the Cl atom to form a sigma bond. So it's not just sp3 for everything, it's sp3 with 3p. So this is what the carbon side, and this is for the chlorine side. And for the carbon hydrogen, the sigma bond is formed by the overlap of sp3 orbital on the atom with a 1s orbital. So we were close, but now it's important to talk about what this means, okay? So what is hydrogen when you look at the electron configuration? We have just 1s1. This is what it means. And for the carbon, the reason why it's sp3 hybridized, that's what we call it, is because of the bonding pairs around it. Okay, so that is the state it's in, which is why the 1s and the sp3, those are what's communicating. Same thing, because all the bonds are the same, that's what carbon is using to communicate with the chlorine as well, which is why here it stays sp3, okay? But if you look at now the electron configuration for chlorine, we have it, actually, as you can see here on the periodic table, it is on the third row, which is why it's 3p, because if we actually did the shorthand notation for it, it'd be neon, and then you go 3s2 3p5. And now you're probably wondering how they know that it's bonding from the p orbital. So for these, we usually assume that exactly we're trying to build from the bottom up. The s orbitals are closer to the nucleus, well, the center of the atom, and so the s orbitals get filled first. Think of the s orbitals on a chlorine as like maybe any two of these electrons. Those are probably what the s orbital. It's already filled. So what it was trying to do was fill up its p orbital. Hence how it had 3p5. And what carbon did was say, hey, I can help you fill those out if you share this electron with me. So while this carbon is sp3 hybridized, that is why it's attached to the 3p and not the 3s. So overall we learned it was 3 from the fact that it is its most outer shell, that is the valence electrons, and it's going to be the p orbital because we said we fill from down up, the lowest energy to the highest energy, and the p was the outer energy to which carbon is going to attach itself to. Hopefully that made more sense in regards to now how they got the answer. It was just hard to get the phrasing out, but I'm just glad we had this basis in order to do so. So now with that being said, let's move on to question number 4.